Hello, welcome everyone. So in today's lecture, we are essentially going to keep continuing with the concept of 2D stress transformation that we started in the last class. We looked at how to transform stresses from one coordinate system to another in the case of 2D stresses. And we also looked at the concept of principal stresses, principal planes, how to find the direction of principal stresses and so on. Okay. So today we will continue with that. We will look at a couple of more concepts. One is the concept of the maximum shear stress, how to find out the magnitude of the maximum shear stress and the direction of the maximum shear stress. And then we will also try to understand what is the relationship between the directions of maximum principal stress and the maximum shear stress. Okay. Okay. So just to kind of recap what we did in the last class, we looked at cases where you, for example, had a point, okay, and you had a stress at a point P. And if you have the stress at that particular point B, a point P, in the XY coordinate system, okay, we learned to find out what the stresses at the exact same point are, at the exact same loading conditions in the X prime, Y prime coordinate system. Okay, that is what we did in the last class. Okay, and the stress transformation equation. So if you know sigma x, sigma y, and tau xy at this point P, for the xy coordinate system, you can find the stress at the same point P in the x prime, y prime coordinate system using these equations 1, 2, and 3. So essentially sigma x prime is sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 times cosine 2 theta plus tau xy sine 2 theta and so on. Okay. One thing that you want to kind of remember in this case is that this theta is always defined as the angle between the x prime axis and the x axis. So if you go from x to x prime, that angle is theta. Okay, it is not defined any other way. So only if you define the theta as the angle between x and x prime, then these equations hold good. Okay, that is something that you must always keep in mind. Okay, so we can transform the stresses to the x prime y prime coordinate system and get sigma x prime, sigma y prime, and tau x prime y prime. Okay, we also know that if you maximize this sigma x prime, essentially we get the principal stresses. Okay, to be more precise, if you maximize or minimize sigma x prime, you get the maximum principal stress and the minimum principal stress. And the way you go about doing that is essentially take the derivative of sigma x prime with respect to theta and set it to 0. And then you then take the second derivative, make sure that it is less than 0. If that is less than 0, then whatever value of theta that you found is essentially corresponding to the maximum principal stress. If the second derivative is greater than 0, then the theta value that you found corresponds to the minimum principal stress. Okay, so that is how you calculate this sigma P1 and sigma P2. We did this in the last class. Of course, this is a 2D stress state. So the third principal stress, sigma P3, is always 0. Okay, so one thing that you must keep in mind is that the sigma P1 and sigma P2 that you are finding are the maximum and minimum principal stress in the XY plane. Okay, we are not taking into account what is happening in the third direction. Okay, we are only looking at 2D cases here. Okay, so this is something that we have already learned in the previous lectures. Okay, so a couple of things I want to note about this equation. So if you look at this equations for sigma x prime and sigma y prime, what you see is that if you add sigma x prime and sigma y prime, what you see is that this term and that term gets cancelled off. Okay. Similarly, this term and that term gets cancelled off. So if you add equations 1 and 2, what you're left with is that sigma x prime plus sigma y prime is equal to sigma x plus sigma y. Okay. So if you look at it, we didn't make any specific assumptions about this x prime y prime coordinate system, which means that it is true for any x prime y prime coordinate system. Okay. So what does it essentially mean? The sum of the normal stresses, okay, at a point in any coordinate system is always the same. Okay, so it is a 2D stress case. So sigma x plus sigma y is going to be equal to sigma x prime plus sigma y prime. If you have another coordinate system, x double prime, y double prime, then sigma x double prime plus sigma y double prime will be equal to sigma x plus sigma y. So this is a constant. Okay, this actually applies even for the 3D case. So essentially, if you look at sigma x plus sigma y plus sigma z, that is going to be equal to sigma x prime plus sigma y prime plus sigma z prime. And this is what is called as a stress invariant. Okay, we will look at this thing in a lot more detail when we go to 3D stress analysis, but it's something that is worth keeping in mind. Okay, so another point is that if sigma x plus sigma y is a constant, then it should be also equal to sigma p1 plus sigma p2, because sigma p1 and sigma p2 are essentially the normal stresses in the principal coordinates. Okay, so you can think of sigma x plus sigma y is sigma x prime plus sigma y prime is equal to sigma p1 plus sigma p2. Okay, so this is something just that is related to the stress transformation equations and the principal stresses. Okay, now we look at the concept of maximum shear stress. Okay, again, this maximum shear stress that we are talking about applies only to the xy plane. So what we are talking about is actually the maximum shear stress in the xy plane. When it comes to 3D stress rate or the maximum shear stress, it is going to be slightly different, and that we will look at when we go to 3D stress analysis. Okay, so let's start with this equation for tau x prime y prime. Again, just to remind you, this is the x direction, that is the y direction, and this is x prime and that is y prime, and we define theta to be the angle between x and x prime. That is something that you must keep in mind. Okay, so the tau x prime y prime is given by this equation here that I just pointed out. Okay, now to maximize the shear stress, you essentially adopt the exact same procedure. So you take the derivative of tau x prime y prime with respect to theta and set it to 0. Okay, this condition essentially tells you this is the condition that is needed for tau x prime y prime to either be maximum or minimum. Okay, in the case of shear stress, the maximum and minimum actually have the same magnitude. It's just the signs are opposite. One will be a positive shear stress, one will be a negative shear stress. Okay, so essentially, if you take this derivative and set it to 0, you essentially get the equation for theta that actually maximizes the shear stress, and that is given by the equation that is a circle. Okay, so if you do that, you essentially get this equation for theta s. To theta s, I have used to use the symbol theta s to denote that this is corresponding to the maximum shear stress, and that is given by like the inverse tangent of minus sigma x minus sigma y divided by tau 2 tau xy. Again, you know that for the xy coordinate system, you know sigma x, sigma y, and tau xy. Okay, and given that information, you can find out at what particular angle you are going to have the maximum shear stress. Okay, so what does it actually mean physically? So if you think about the point P here, okay, and then you have the stress defined at that point, sigma x, sigma y, and tau xy, okay, then if you take this particular square and then you rotate it about the z-axis by this angle theta s1, okay, then you essentially get a square that is inclined like this. And if you look at that particular square and you look at the shear stresses on the faces of that particular square, then that particular value is tau max. So essentially, the maximum shear stress occurs on these planes here. This plane, that plane, that plane, and that plane. Okay? And again, I want you to remember, shear stresses always point towards each other. So if there is a shear stress on this plane like that, there has to be a shear stress on that plane like that. And this is required to satisfy moment equilibrium. Okay? And this was the basis for the complementary property of shear that we looked at a couple of lectures back. Okay? So similarly, you have a shear stress on this plane and a shear stress on this plane. Okay? So all the shear stresses are obviously equal, and they actually have the maximum value is just tau max. Okay. One big difference between the planes where you have the maximum shear stress and the planes where you have the maximum normal stress, which are essentially the principal planes, is that on the principal planes, the shear stress is 0. Okay. On the other hand, when you have planes with the maximum shear stress, the normal stress on those planes are not actually equal to 0. They essentially have a value of sigma. We'll look at what that value is in a second. Okay? So that is a big difference. On the principal planes, shear stress are 0. On the planes where the shear stress is maximum, the normal stress is not 0. Okay. So now I told you that this is theta S1. Okay. These are the 4 planes where you have maximum shear stress. Okay. Theta S2, okay, which is the planes where the maximum shear stress, the shear stress is minimum, that is given by this theta S2 equal to theta S1 plus 90. What it actually means is that you essentially rotate this square here by another 90 degrees. Okay. So what actually you're ending up doing is that you're changing the coordinate system. Now this is your x prime, that corresponds to tau max, okay, just as I have noted here. You now take this x prime and make that x prime, okay. If you do that, essentially the sign of the shear stress changes, okay, but the magnitude remains the same. Okay, so when it comes to maximum shear stress, you usually worry only about the magnitude of the shear, not about the sign, okay, because that is what matters. Okay, so this is how you calculate the maximum shear stress. Okay, now just to kind of reinforce the point, the planes on which the maximum shear stress occurs are not the planes where the maximum normal stress occurs. So in other words, the maximum shear stress plane and the principal planes are not the same. They are different. But there is a relationship between those. The maximum shear stress plane is essentially at 45 degrees to the maximum normal stress plane or the principal plane. Okay? So if you think of the plane where the maximum principal stress occurs, then the maximum shear stress plane is at 45 degrees to that. Okay, so that is something that is important to keep in mind. And the second thing which I have already noted is that on this maximum shear stress planes, the normal stress sigma is not 0, rather it is equal to sigma x plus sigma y divided by 2. Okay, so essentially it's the average of the normal stresses in the xy coordinate system. Okay, so that is something that you must keep in mind. Okay, so these are the main differences between maximum shear stress and the principal stress, and the maximum shear stress planes and the principal planes. Okay, okay. So now we have talked a lot about how to find the maximum normal stresses, which are essentially the principal stresses, and the maximum shear stress. Of course, you can always use the stress transformation equations to find them, but they're also easy to derive and come up with like fairly compact equations for these principal stresses and maximum shear stress. So essentially, you use the stress transformation equations, find out for which theta sigma x prime is maximized, and then you put that theta back in the sigma x prime equation, you get sigma p1, which is the maximum principal stress, or principal stress number 1. And if you do that, this is the equation that you get. Okay? So that is the equation for the maximum principal stress. So these are compact equations because you have already the knowledge of sigma x, sigma y, and tau xy. You essentially plug it into these equations, you get sigma p1, sigma p2, and tau max. Okay? So sigma p1 is the maximum principal stress, sigma p2 is the minimum principal stress, and tau max, of course, is the maximum shear stress. One thing, if you look at these equations here, is that if you look at sigma p1 and sigma p2, the first term is essentially the same, sigma x plus sigma y divided by 2. The second term is the same, but with opposite signs. So the second term is plus square root of sigma x minus sigma y by 2 the whole square plus tau xy square for sigma p1. And it is minus of that square root term for the sigma p2 term. Okay? So if you look at these two equations, you add them up, you will see that the second term cancels off. So it becomes again sigma p1 plus sigma p2 is sigma x plus sigma y. Okay? That is essentially what I told you earlier on as well. Okay. Now, tau max is essentially the difference between sigma p1 and sigma p2 divided by 2. So sigma p1 minus sigma p2 divided by 2 is going to be equal to just the square root term, and that is what is given here. Okay, so that is going to be your maximum shear stress. And of course, the minimum shear stress is nothing but the maximum shear stress with a negative sign. Okay, so again, to reinforce a few things, when you look at principal planes, the shear stress is 0. On the maximum or the minimum shear stress planes, the normal stress is sigma x plus sigma y divided by 2. Okay. There's also another point that I want to really emphasize, and this is something that you must really keep in mind, is that all these equations that we derived here or that I have written here, right? These are true for the 2D stress case. And more importantly, the sigma P1 and sigma P2 and tau max that we calculate are the maximum and minimum principal stresses and the maximum shear stress in the XY plane. Okay? We are not considering the third direction at all. So these are all true only for the XY plane. Okay? When you have stresses in the third direction, things become different. Okay? So your sigma P1, sigma P2, sigma P3 have to be derived in a different manner. Okay? And even in this case, the sigma P1 and P2 are again maximum and minimum principal stresses in the plane. Okay? So one thing that you can obviously see is that because it is a 2D stress state, sigma P3 is 0. Okay? Now, sigma P1 can be negative. So if you look at the equation here, this one, okay, if sigma x is negative, sigma y is negative, okay, and tau xy is reasonably small, then sigma P1 will be negative, okay, and sigma P3 we know is 0. So sigma P3 is actually greater than sigma P1, okay. So this is something that you must keep in mind. All we can say is that sigma P1 will be greater than sigma P2, okay. We don't know whether it will be greater than sigma 3. Okay, of course, once you calculate, you can find out because sigma 3 or sigma P3 is actually equal to 0. So all these equations are only true for the 2D stress case where you have only stresses in the XY plane, okay, and the sigma P1 and sigma P2 are the principal stresses in the XY plane, okay. So the same thing is true for the shear stress or the maximum shear stress. I have written it as sigma P1 minus sigma P2 divided by 2. This is the maximum shear stress in the plane. Okay? When it comes to a 3D case, tau max is actually going to be sigma P1 minus sigma P3 divided by 2, okay, where we order the max or the principal stresses as sigma P1 greater than sigma P2 greater than sigma P3. Okay? Once you make this ordering, then you can use this formula. Okay? But this formula that we have here holds good only for the 2D case, and this is the maximum shear stress in the plane. Point blank. Okay? So when you go to the 3D stress case, we will have a much more general method of calculating the principal stresses, the 3 principal stresses and the shear stress, and that you can use for any condition. But these compact equations that we have here is true only for the 2D case, something that I really want to emphasize and something that you must keep in mind. Okay? So if you want to kind of look at this whole picture, okay, what we have learned so far when it comes to 2D stress transformations and principal stresses and maximum shear stress is that, say suppose you have a point P here. Okay, this is some point inside a body, okay, and this particular point has a 2D stress state, which means that it has only stresses in the x and y directions, sigma x, sigma y, and tau xy. There is no z component stresses. Okay, you're looking at this particular point. Okay, you define a square or a cube, whichever way you want to look at it, around that particular point. You find out, you know what the stresses are, sigma x, sigma y, and tau xy. Now, you rotate this particular square about the z-axis, which is coming out of plane, by an angle of theta p1, okay, which corresponds to the first maximum principal stress. And what you see is that this plane and that plane will essentially have the maximum principal stress sigma p1. The orthogonal planes will have the minimum principal stress sigma p2. Okay? And all these 4 planes will basically have 0 shear stress. Okay? Now, you take this rotated square and then rotate it further by another 45 degrees. Okay? Then you essentially get to the maximum shear stress planes, these 4. Okay? And on this maximum shear stress planes, the normal stress is sigma x plus sigma y divided by 2. Okay? Or I have written it as sigma prime here, but that essentially is the normal stress on the maximum shear stress plane. That essentially kind of gives you the overall picture of this principal stresses and principal planes and maximum shear stress and the maximum shear stress plane. Okay, so something that is important to remember is that we are looking at the exact same point. We are not looking at any other point. We are not changing the loading. We are not looking at a different body. Everything is the same. All we are doing is that we are rotating the coordinate system about that particular point. Okay? And as we rotate this coordinate system, the stresses on the planes will essentially keep changing. So first, you get to the maximum principal stress planes, and then you rotate further, you get to the maximum shear stress planes. Okay. And another thing, a final point that I want to make is that in all these cases, I have said that I have kind of drawn them in such a way that the rotations are positive. So essentially, I am rotating in a positive direction, or counterclockwise direction about the z-axis. Of course, they can be in the negative direction. So instead of starting with a figure like this, you can actually go to a figure like that, where this is going to be your sigma p1, and that is sigma p2. Okay, that is definitely possible. So in this case, the theta will be negative. Okay, or this theta p1 will be negative. Okay, so that is certainly possible. So I have just drawn this schematically in this particular manner so that it is easy to see. Okay, so obviously theta p1 can be negative. Theta p2 of course can also be negative, and so on. Okay, so this essentially kind of summarizes the concepts of principal stresses, principal planes, maximum shear stress, and the maximum shear stress planes. So in the next lecture, we will look at some examples of using these equations. First, to look at finding stresses in different planes, and then later on we'll look at how to find principal stresses for specific cases. Okay. With that, I will conclude this lecture and see you in the next lecture. Thank you.